Hi friends, can you tell me who is the famous scientist who challenged the great Albert Einstein? He has an element named after him and he won the Nobel Prize for his amazing work on the structure of the atom. That's right, the answer is Niels Bohr, and in this video we are going to look at Bohr's atomic model. I'm going to explain the postulates of the Bohr's atomic model and make these concepts absolutely clear for you. So make sure you watch the video till the end. And before we begin, I just want to say, do check out the full courses on our website manochaacademy.com and our Android app Manocha Academy. To make it easy, I'll put the links below. Alright, let's dive into Bohr's atomic model. Various models of the atoms have been proposed by the scientists over the years. And every time a model was proposed, after some years, scientists would do experiments and disprove the model. And then again, they would propose a new model. So let's take a look at the various atomic models. It all started in 1807, where Dalton proposed the model of the atom, where he considered it as a solid sphere. So just like a tiny ball, a tiny sphere. And this model was there for many years. In 1897, Thomson proposed a new model of the atom after the discovery of the electron. This was called the plum pudding model, where the atom was thought to be a large positive sphere, and in that these tiny negatively charged electrons were embedded like plums in the pudding. But this model was disproved by Rutherford when he did his famous alpha scattering experiment. And he said that the atom doesn't contain a large positive sphere of charge, rather the positive charge is concentrated in a very tiny area called the nucleus of the atom. And that's why this came to be known as the nuclear model of the atom, and the electrons are spinning around this nucleus. But then there were drawbacks of Rutherford's model, and Niels Bohr came up with a new model of the atom, which is called the planetary model, where electrons revolve in certain orbits or shells. So we'll talk about the drawbacks, and in this video we'll focus on Niels Bohr's model of the atom. And many years later, Erwin Schrödinger, he proposed the quantum model of the atom, where the electrons are considered as waves. But in this video, our focus is going to be on the Bohr's model of the atom. So let's dive into the Bohr's model of the atom. Now, before we look at Bohr's model of the atom, let's talk about what was wrong with Rutherford's model of the atom. So why did Bohr propose a new model? Let's take a look at the drawbacks of the Rutherford's model of the atom. So the first drawback was it could not explain the stability of the atom. Why is that? Because according to Maxwell's electromagnetic theory, when electrons are revolving around the nucleus, you basically have charged particles revolving around the nucleus, right? Because electrons are negatively charged. And according to Maxwell's electromagnetic theory, when a charged particle is under acceleration, it will give out energy. So are these electrons accelerating? The answer is yes, because even if the electrons are moving at constant speed, they are going in a circular motion. This means the direction of their velocity is constantly changing, right? Because when the electron revolves around the nucleus, its velocity will constantly be changing. See the direction of the velocity. And what is change of velocity known as? That's right, acceleration. So we know that these negatively charged particles, these electrons, are accelerating. And according to Maxwell's electromagnetic theory, this means that they are going to radiate energy. So these electrons are going to give out energy. And if the electrons are giving out energy, that means they're losing energy. And if a moving particle is constantly losing energy, what's going to happen, guys? That's right. It will slowly lose energy and boom, it will collapse into the nucleus because it is losing energy and it will start falling down into the nucleus. This means if all the electrons start falling into the nucleus, the atom will go boom. It will not be stable. So basically, Rutherford's model had a big drawback. It could not explain the stability of the atom. We know that the atoms are stable. Otherwise, you and I won't exist, right? We are made up of atoms, or this entire digital board will collapse here. So that is not true, and Niels Bohr wanted to rectify this. Another very important experiment Rutherford's model could not explain is that this observation of line spectrum or atomic spectrum. For example, if you take the hydrogen element, the hydrogen gas, when heated or under electric discharge, gives these kind of lines, this kind of spectrum. Can you see here? We all know spectrum is continuous, right? It has all these Vibgyor colors if you're looking at the visible spectrum. But a certain gas like hydrogen or any other element, it would give out only certain colors like this. And this could not be explained, that why are we getting only certain bands of colors from hydrogen. This could not be explained by Rutherford's model. So these were the drawbacks of Rutherford's model, and let's take a look what was Niels Bohr model and how they rectified this. So Niels Bohr, the famous scientist who challenged Albert Einstein, that's right, he had many debates with Albert Einstein. Both of them really admired each other, but they had a lot of scientific debates, and Niels Bohr was the scientist who challenged Albert Einstein. So he came up with the model which is called the Bohr atomic model. Now, what is the Bohr atomic model? You can visualize it like this, right? Where once again, like Rutherford, there is a nucleus which contains the positive charge, and now we know that it contains protons and neutrons. But at that time, neutrons weren't discovered. So they said there is a positive charge in the nucleus. And then he said that electrons revolve around in certain fixed orbits, what are known as shells. So electrons are revolving around the nucleus in fixed orbits known as shells, or you can call them orbits. So this is the visualization you should have of Bohr's atomic model, and let's go ahead and discuss what were the important points or what were the postulates of Bohr's model. Here are the postulates of Bohr's model. The first postulate says that electrons revolve around the nucleus in fixed circular orbits, like we saw in the picture there, and these orbits have a fixed radius and fixed energy. So I'm going to go through these points, and don't worry, we'll be discussing each and every point in detail. So let's take a look at all the postulates first. So that was the first postulate. Second postulate, there's a very interesting quantization condition. So he said electrons cannot revolve in any circular orbit, any random orbit. No, they revolve only in those circular orbits where the angular momentum of the electron is nh by 2 pi. So integer multiples of h by 2 pi. And we'll also talk about this in detail later. The third postulate says that electrons can gain or lose energy, and when they do that, they will move to the higher shell or they will come down to a lower shell. So it's possible for electrons to gain or lose energy, and when they do that, they will change their shells or orbits. Okay, so remember, they can gain or lose energy, but only when they are moving from one shell to the other. And frequency of radiation that can be absorbed or emitted, because when they are making this transition, when electrons are moving to a higher shell or coming down to a lower shell, then the frequency of radiation absorbed or emitted is given by this formula. The frequency equals to the change in energy divided by h, and h is Planck's constant here. So let's look at each of these postulates one by one in detail. Let's look at the first point of Bohr's atomic model. The first postulate states that electrons revolve around the nucleus in fixed circular orbits of fixed radius and fixed energy. So let's understand what he meant by this. So we know that the atom, and that was from Rutherford's model, we know that the atom has a positively charged nucleus. So this positive charge is concentrated in this nucleus in the center of the atom, and electrons are revolving around the nucleus. But what Niels Bohr said, that when electrons are revolving around the nucleus, they cannot revolve in any random place. So electron cannot be here, here, anywhere, right? It has to revolve around in orbits having fixed radius. That means this radius, we can call it R1, is fixed. So electron must be here, right? If it wants to go to a higher radius, it cannot go in the middle. It must go to the next radius, which is, let's say, at R2. Similarly, this one is at R3.
And all these orbits are circular orbits. So basically, electron can't say that, hey, I want to roam around here, hey, I want to roam around there. No. So nucleus is like its parent. It says, no, you must go in this circle, or in this circle, or in this circle. So these are fixed radius, and these electrons are revolving with the fixed amount of energy, right? So for example, it has certain electron volts of energy in this first orbit that is fixed, right? If it has a different amount of energy, it will be in the next orbit. But this amount of energies are fixed. And these orbits is what Bohr called them as shells. So remember, he had called these orbits as shells and labeled them as K, L, M, and so on, where basically K is the first shell, L is the second shell, M is the third shell, and so on. So one very important term he had used, these are called shells or orbits. And so his model is very similar to the solar system, or we can say the planetary model, because in the solar system we know sun is at the center, okay, and the planets are revolving around in fixed orbits. So Earth can't tell Mars that, hey, I'm going here, right, or I'm going there. It's revolving around the sun in a fixed orbit. So same concept applies to the atom here. So these are all planets are revolving around in a fixed orbit with fixed energy. Same logic he applied here to the atom. Okay, so remember this very important point that electrons revolve around the nucleus in fixed circular orbits having fixed radius. Okay, radius is fixed and the energy of the electron in the orbit is also fixed. So we have discussed the first point of Bohr's atomic model. Now let's look at his second postulate. Second postulate is very interesting because he said there is a quantization condition. And what is that quantization condition? That electrons revolve in only those circular orbits where the angular momentum L is nh by 2 pi. So there is a condition for where the electrons can revolve, and this condition is based on the angular momentum of the electrons. It is an integer multiple of h by 2 pi. So to really understand this postulate of quantization condition, first we need to understand what does this term angular momentum means. So let's take a look at what is angular momentum. So what is angular momentum? Angular momentum, you can remember, is the moment of the momentum. Now what do I mean by that? Moment means you're multiplying the momentum p with the distance. And if we talk in terms of vector notation, angular momentum is denoted by L is the cross product. It's the vector product of r times the momentum p. So let me explain it with a simple example. Let's say the electron is revolving in a circle like this. So here is our Mr. Electron who's going around in this circle. And we want to find the angular momentum of that electron. So first of all, the electron has a momentum. What is momentum? Mass times velocity. Okay. So we know that this electron will have a momentum, mass times velocity, mv. And what is angular momentum? Angular momentum means the moment of the momentum, which means you're multiplying the distance times the momentum p. Okay, so if we are considering from the center here of the circle, and we can say the circle has a radius r. So this cross product of the radius with the momentum is called the angular momentum of the electron. This is the momentum p, and this is our distance vector here where we are considering the moment of that momentum. So when we are doing a cross product of these two, remember the cross product you have to take a rp sine theta, but here the angle between the momentum and this radius vector, this r over here, is basically 90 degree. So sine of 90 you know is 1. So we can simply take it as r times mv. So angular momentum is going to be this r, the distance here from the center. So this is my center O, times the momentum of the electron mv. So we don't need any sine theta term. So you can simply remember that your angular momentum L is going to be mv times r. What is m? Mass of the electron. V, velocity of the electron. And r is the radius in which it is going. Okay, because we are measuring the momentum, the angular momentum along this circular orbit. So r is the radius here. Clear? So that is basically your angular momentum formula. And this is where Niels Bohr said that this angular momentum cannot be any general value. It cannot be any random value. There is a certain quantization here. What do we mean by that? That it must be integer multiples of h by 2 pi. Because this n over here, n means it is an integer. So it has to be integer multiples of h by 2 pi, where h is Planck's constant and pi you guys know, right? The irrational number which we approximate to 22 by 7. So this is what Niels Bohr said is the angular momentum MVR should be integer multiples of h by 2 pi. So either it can be 1 times h by 2 pi or 2 times h by 2 pi or 3 times h by 2 pi and so on. But you cannot have it like 1.1, 1.2, 1.3 or 2.7. No random values like that, right? It has to be integer multiples of h by 2 pi. So that is why we call this like a quantization condition. Like you can only go in certain steps. So the angular momentum, again I'm repeating, has to be integer multiples of h by 2 pi. Very, very, very important equation. Please note this down. And this is a very important concept that Niels Bohr proposed. And that's why he said that these electrons revolve in these fixed orbits, in these certain shells. You cannot randomly put an electron anywhere in the atom. No. It must satisfy this condition that MVR equal to NH by 2 pi. Okay. And let's also note down what these are. So as I told you, H is Planck's constant. Pi you guys know. And this n integer is basically the shell number. So when for first shell, n equals 1. For the second shell, n equal to 2. For the third shell, n equal to 3. So note this down. N is basically your integer, is basically your shell number, which can be 1, 2, 3 and so on. For the K, L, M, N shell and so on. Okay, remember? So this n integer is basically your shell number in Bohr's model of the atom. Now, how is the electron revolving around the nucleus? It's just like our solar system. In the solar system, you have the sun at the center and planets revolving around it. And it is sun's gravitational force, the gravitational pull of the sun, that is making the planets revolve there. But in case of nucleus and electrons, it is not the gravitational force, it is the electrostatic force. What is electrostatic force? You must have studied this in physics. Electrostatic force is the force between two charged particles. Now, who are the charged particles here? In the atom, we know that nucleus is positively charged. So there's a positively charged nucleus. And then you have the electron, which is negatively charged. So clearly there is a force of attraction between the positive and negative charge, because remember we know that unlike charges, they attract each other and like charges repel each other. So there will definitely be a force of attraction between the nucleus and this electron. And this is called the electrostatic force. And it is this electrostatic force or this electrostatic pull that is continuously making the electron revolve around the nucleus. Now, what is the formula of the electrostatic force? From physics, we know electrostatic force is 1 by 4 pi epsilon naught Q1 Q2 by R square. So lots of symbols over there. Don't be scared. I'll explain what they mean. Q1, Q2 are the charges. So here it's going to be the charge of the nucleus and the charge of the electron. R is the radius, right? The distance between the two charges. So this will be your R, the radius of the orbit, or you can say the distance between the nucleus and the electron. And epsilon naught is the permittivity of free space. So it is a constant over here and it is called the permittivity of free space. And then of course you have your pi, 22 by 7 approximately. So this is the electrostatic force formula between two charged particles, Q1 and Q2. So we can say that this is our Q1, this is the Q2. Now, since the electron is going in a circular orbit, right? It is in circular motion around the nucleus. We can also say that there is a centripetal force, right? That is making it go round and round. Why is it called centripetal force? Because it is a center-seeking force. This force is always pointing towards the center. So whether the electron is there, or if the electron is here, or if it is here, or if it is here, we know that there will always be a center-seeking force pulling it towards the nucleus, because there is an attraction between the nucleus and the electron. And this is what we call as our centripetal force, denoted by Fc. So who is the centripetal force? It is the electrostatic force which is the centripetal force here, because electrostatic force is the pull between the nucleus and the electron, and that is acting like the centripetal force here. Just like in solar system, the gravitational force, the gravitational pull of the sun is the centripetal force for the planets. Here the electrostatic force is the centripetal force for the electrons. So we can say Fe equal to Fc. The electrostatic force is the centripetal force. And from physics, we know what is the centripetal force formula. If a particle of mass m is going around in a circle of radius r with a velocity v, the centripetal force Fc is given by mv square by r. So we can equate these terms over here, because this is the electrostatic force formula, this is the centripetal force formula, and we know that they're going to be equal because the electrostatic force is the centripetal force over here. As we discussed, the electrostatic force between the nucleus and the electron equals to the centripetal force. So if we apply the formulas of electrostatic force and centripetal force, what does the expression become? Remember, electrostatic force is 1 by 4 pi epsilon naught Q1 Q2 by r square, and centripetal force is mv square by r. Now let's go ahead and substitute the values for Q1 and Q2. Remember, what is our model? In the center we have a positively charged nucleus, and then we have this electron, negatively charged electron, revolving around the nucleus. So what is the charge of the electron? Electron, we know it has a charge which we denote as E, or it has a negative charge of E. And what is the charge of the nucleus? How much will the nucleus be charged? And that equals the number of protons present in the nucleus. Now, how many protons does a nucleus have? It is called atomic number in chemistry, which we denoted by Z. So the charge of the nucleus is going to be Z times E. Because remember, electron and proton have the same charge, and it has atomic number of protons in it, which is denoted by Z. So charge of the nucleus is plus Ze, charge of the electron is minus E, right? So if we go ahead and substitute these values as Q1 and Q2, so let's say our nucleus is Q1, the charge of the nucleus is Q1, and charge of the electron, which I represent as Q2. So if we put this into our equation, what are we going to get here? We are going to get 1 by 4 pi epsilon naught. For Q1, I'm going to put Ze, and for the electron, I'm going to put E. So Ze multiplied by E divided by r square equals mv square by r, the centripetal force. So now go ahead and simplify this. So what will you get over here? 1 by 4 pi epsilon naught. And this is going to give me a Ze square divided by an r square. And that equals mv square by r. So remember, we are equating the electrostatic force equal to the centripetal force, the center-seeking force for an electron spinning around the nucleus. Now let's see if we can find the expression to calculate the radius of the electron. So what will we do for that? We can make use of the equations that we have seen before. The first equation, remember, angular momentum is integer multiples of h by 2 pi. And the second equation, how did we get? By equating the electrostatic force equal to the centripetal force. I know these formulas look a little complicated, but don't worry, the concepts are very simple. You're equating angular momentum to nh by 2 pi, and here electrostatic force equal to your centripetal force. Now our goal is to get an expression for the radius r. So how do we do that? So you can see there's a radius r over here in this equation, and we have r square and r over here. But who do we want to get rid of? We want to get rid of the velocity, because we have a v over here, we have a v square over there. So I want r and all the other things, because the other things are usually constant, or they are simple things like atomic number or your shell number. So our basic goal here is to get rid of the velocity term v. So you can use the math trick over here. If you want to get rid of velocity v, you can see we have a v here, we have a v square. So let's square the first equation, and then we can divide the two equations, so v square will get cancelled, right? So come on, go ahead and square equation number 1. So I'm going to square equation number 1, which means we are going to be squaring this equation, square the left hand side and right hand side. So what do we get? We are going to get, on the left hand side, it's going to be n square h square divided by 2 pi square, which is basically 4 pi square, equal to m square v square by r square. Okay, so see, we have squared both the sides of the equation. Now what we are going to do is, we are going to divide this equation, the square of equation 1, with equation number 2. So if you want to call this equation number 3 here, we will divide these two equations. So we can say dividing. So we can say dividing equation 3 with equation number 2. And if you do that, what will you get? So take a look. So when we are doing the division, n square h square divided by 4 pi square, and here you have m square v square by times r square. And if I want to divide, I'm going to get a 1 by 4 pi epsilon naught z e square by r square. And this side, when we divide, we'll get a mv square by r. So this is what we have here. Now see what stuff can get cancelled out for you. So see, v square, this was our goal, to get rid of the v square. So v square and v square is gone. And here we can see the 4 and 4 will go away. You have a divided by pi square divided by pi. So 1 pi is going to go away here. What else can we cancel here? 1m, and this 1m will go away. And the r will come on top. I can't cancel the r. So let's simplify this equation that we have over here. So we are basically getting n square h square divided by pi, and r, since we are dividing by this, we'll take the reciprocal. So this will go on top here. So we'll get a epsilon naught r square divided by ze square. And on the right hand side, what do we have? We have a m r square, and this r goes on top, so it becomes a m r cubed. So once again, r square and r cube will cancel, so we are just left with an r. So that's exactly what we wanted. So if we simplify this and bring r to one side, we are basically done. So what are we getting? The radius r of the electron, r equals n square h square epsilon naught divided by m pi ze square. So this is the final expression for the radius. See, velocity is no longer over here. And now let's take a look. What are all our constants over here? So for any radius Rn, so for the nth shell, what will be the constants? Let's take them out. We know Planck, h is Planck's constant. So that is h square, that comes out. Epsilon naught is a Permittivity of free space, that's a constant. We take that out here. Mass of electron is constant, so m. Pi is a constant, and so is E square. Or I can write it as pi m mass of electron times E square, which is the charge of the electron squared. And here we are left with n squared by z. Remember, n is the shell number and z is the atomic number of the atom. So see, I brought all the constant terms here. So Rn is all these constant terms multiplied by n squared divided by z. Now you'll say we have to remember all these complicated expressions. Yes, at least you should know the derivation, and it's good for you to learn this expression. But then there is a shortcut here that we can put all these constants, because all the constants, if we substitute their values, then we can get a shortcut or simplified expression, which I'm going to give you. So if you substitute all the values over here, you're going to get finally your equation will become Rn is 0.53 n square by z. And this is the radius of the electron in angstroms. Remember, angstrom is 10 to the power minus 10 meter. So if you substitute all this Planck's constant, epsilon naught, pi, m, E square, all this in your SI units, finally you're going to end up with this important expression that the radius of the nth shell, Rn, is 0.53 times n square by z, where n is the shell number and z is the atomic number. So this is a very, very important formula where we have derived the radius of an electron. So let's use the radius formula and calculate the radius of the hydrogen shells. So remember, our shortcut formula was Rn, the radius of the nth shell or the nth orbit, is 0.53 times n squared, the shell number, squared, divided by z, the atomic number. And remember, this radius is in angstrom. You guys remember that 1 angstrom is 10 to the power minus 10 meters. Okay, that is the value of 1 angstrom. So let's see what will be the radius of the hydrogen's shells. So if you consider the first shell, what will be that radius? So you just have to substitute n equal to 1 over here. So first shell means n equal to 1. So we can say R1 equal to 0.53 times 1 square. And what is the atomic number of hydrogen? Atomic number means the number of protons present in the nucleus. And we know hydrogen has the atomic number of 1. So let's put Z equal to 1 here. So once we substitute these values, we'll get R1 equal to 0.53 angstrom, the radius of the first shell. Now why don't you work out the radius of the second shell of the hydrogen atom? Second shell, very easy. We'll substitute n equal to 2 here. So we are calculating R2, guys. What is that going to be? 0.53 times 2 square divided by, again, the atomic number of hydrogen is 1. So divided by 1. So you do this calculation. So it's basically 4 times 0.53 angstrom. So if you multiply these numbers, you'll finally get 2.12 angstrom, the radius of the second shell. Now let's work out the radius of the third shell. Very simple. Here you just have to put n equal to 3. So what will be your radius be? R3 equal to 0.53 multiplied by 3 square divided by 1. So you need to do 9 times 0.53. If you multiply 9 times 0.53, you will get, so you will be getting 4.77 angstrom. And similarly, you can do it for the fourth shell, fifth shell. So basically our nth shell, Rn, is what? It is 0.53 times n square. And since the atomic number of hydrogen is 1, it's divided by 1. So this is the expression. You can find out the radius of any of the shells in the hydrogen atom. And as expected, as the shell number is increasing, you can see the radius is increasing. In fact, it is increasing quite fast because there is an n square over here. Now, Bohr's model, one important thing to note is it works for hydrogen atom and single electron species, which means the atom or the particle should have only 1 electron. So strictly, it is not valid for all the atoms. So you'll say, can I use it just for hydrogen? No, you can also use it for helium, but not the helium atom because that has 2 electrons. You'll use it for the helium ion. So if I give you an example of, if you have to work out the radius of He plus ion, because He plus will again have 1 electron. So what will be the formula? Rn equal to 0.53 times n square by z Armstrong. So here let's say we want to work out the first shell. What will it be? R1 equal to 0.53 and n square is 1 divided by what is the atomic number of helium? Z is 2. So you need to substitute 2 over here. So if you do the division 0.53 divided by 2, you will get 0.265 angstrom. So see, you can use Bohr's model for He plus, or you can also use it for lithium plus plus, because once again, it will have atomic number, you substitute Z equal to 3, but the number of electrons is 1. So it is valid for these single electron species. So this is very useful formula where we can work out the radius of the electron shell, and this is the shortcut trick 0.53 n square by z angstrom. We have discussed how to work out the expression for calculating the radius of the electron and also the shortcut formula. Now let's look at how we can calculate the velocity, that is the speed of the electron. So once again, we are going to use these two equations that we learned. Remember, angular momentum mvr equal to nh by 2 pi, integer multiples of h by 2 pi. And here you have r equal to n square h square epsilon naught divided by pi m z square. This was the expression we derived for the radius of the electron. So now our goal is to find out the velocity formula. So what will we do? Very simple. We are going to substitute this r. We are going to substitute this r into the first expression, and that way we'll get the velocity in terms of all these constants, and I think we'll have a z and n also. So let's go ahead and do it. So if you substitute r in equation number 1, what are you going to get? We are going to get mv and r will be n square h square epsilon naught. I know these formulas are a little scary. Pi m z square, and on the right hand side we have nh by 2 pi. So guys, let's see what we can simplify over here. Pi and pi cancels out, so that's good. Please note that this is not a 2, this is a z, so I need to write it clearly. That's a 2. We have h, which is Planck's constant, so h and h square, so h gets cancelled over here. N square and n, 1 n gets cancelled. Anything else, guys? The mass and mass of the electron gets cancelled here. I think that's it. So now let's simplify this expression. So what are we finally going to get here? So we can say the velocity of the electron v equals, so I'm going to take everything to the right hand side, z square will go on top, divided by, so again this is not 2, this is z. Okay, this is z. You can write it clearly over there. So ze square divided by, we have a 2 times this h epsilon naught n. I like to write it like this, H-E-N, so you can remember 2 hen, right, the animal hen. So Z square by 2 hen is what we have here. This is the expression for velocity of an electron. Again, what is Z? Z is atomic number, E is the charge of the electron, that 1.6 times 10 to the power minus 19 coulomb. 2, constant, H is Planck's constant, 6.636 times 10 to the power minus 34 joules second. Epsilon naught is the permittivity of free space, and n is the nth shell. So this is really the velocity of the electron in the nth shell, right? This n is the shell number here. Again, this formula is complicated. So what is the shortcut? Shortcut is if you substitute the values of all these constants. Who are the constants? 2, h, permittivity of free space, charge of electron. These are all constants. N and Z can vary according to the atom because the shell number or the atomic number can change. So if you substitute all these constants, you're finally going to get the formula 2.18 times 10 to the power 6. So all these constants I've substituted and I'm left with Z divided by N. This is the very, very important expression for velocity of the electron in the nth shell, and the unit over here is going to be meters per second. The SI unit, the speed of the electron. So this is your velocity formula for the nth shell of the electron. So let's say we want to find the velocity of the electron in the hydrogen atom. So we can use that shortcut formula that we learned, that the velocity in the nth shell is 2.18 times 10 to the power 6 Z by N. In the hydrogen atom, we know atomic number Z equals 1. And if you are talking about the electron, which is in the first shell, we are going to substitute N equal to 1. So simply these will be 1. So obviously we are left with 2.18 times 10 to the power 6 meter per second. So the electron in the first shell is going at a pretty high velocity of 2.18 times 10 to the power 6 meter per second. Because you know what is speed of light? Speed of light is 3 into 10 to the power 8 meter per second. So this is like 100 times approximately, or little less than 100 times slower than speed of light. So electron is going very fast in the hydrogen atom, or in fact in any of the atoms, the electrons have a very high speed, and you guys can calculate that using this velocity formula. Next, let's take a look at this example. If you have been asked to find the velocity of the electron in the second shell of helium ion, okay, because remember these Bohr's formulas, they work for single electron species, and helium atom, you know, it has 2 protons. So helium atom has 2 protons and 2 electrons, but if you take out 1 electron, He plus ion, you're left with only 1 electron. So let's go ahead and apply the formula. For the helium atom, or for the helium ion, if we want to find the velocity in the second shell, that means I'm interested in V2. It's going to be 2.18 times 10 to the power 6 multiplied by Z by N. So what is N going to be here? N is going to be 2. And what is the atomic number of helium? Atomic number is the number of protons in helium, 2 protons. So we are going to substitute Z also as 2. 2 and 2 will get cancelled. So we get the same velocity as the hydrogen atom, 2.18 times 10 to the power 2.18 times 10 to the power 6 meter per second is the velocity of the electron in the second shell of the He plus ion. So we have talked about the formulas for radius of the electron, the velocity of the electron. Now let's look at the kinetic energy of the electron. What is the meaning of kinetic energy? The energy in motion. And we definitely know that the electron is in a very fast motion. Kinetic energy formula you have learnt in physics. It is half mv square, where m is the mass of the electron, v is the velocity of the electron. So if you want to get the kinetic energy in terms of all these symbols that we have discussed, what do we need to do? Just substitute the velocity formula into this kinetic energy formula. That's it. So substituting this V in the kinetic energy formula, I am going to get kinetic energy equal to half m, and this V square will be this entire thing. So we'll just square this entire expression, Z square, E square to square, which means e to the power 4, divided by 2 square over here. So that's going to be 4h square, epsilon naught square, n square. Wow, lots of squares over here. So if you simplify this expression, again, bring all the constants to one side, what do we get? We are getting m e to the power 4 divided by 8 h square, epsilon naught square, and then we have your z square by n square. This is your kinetic energy in the nth shell. Remember, n is the shell number. So kinetic energy of the electron in the nth shell is given by this complicated expression. Again, don't get scared, because you saw the derivation was very easy. If you knew the velocity formula, you just substitute it here, you will get this expression. And again, see, these are all the constant terms. And this depends on your atom. Z is the atomic number, N is the shell number that you're talking about. Again, there's a shortcut trick here. So the scientists have gone ahead and substituted all these values. And so we know that if you work out this expression, The shortcut formula is kinetic energy in the nth shell is going to be 13.6 Z square by N square electron volts. So the unit here used when substituting the values, we have got kinetic energy in terms of electron volts. If you want it in terms of joules, you have to multiply by the charge of the electron, 1.6 times 10 to the power minus 19, then you'll get it in joules. So it's very small amount in joules because the mass of electron is very small, right? Kinetic energy not only depends on the velocity, it also depends on the mass of the particle, mass of the electron. So these are your important formulas for kinetic energy in the nth shell, the generic formula. And once you substitute the values, you get it in terms of Z square and N square. So this is your kinetic energy of the electron in the nth shell of the atom. We have talked about kinetic energy of the electron, but the electron also has potential energy because we know that there is a pull between the nucleus and the electron. So there is an electrostatic field here, and definitely there is a potential energy also of the electron. Now from physics, we know what is the potential energy formula. It is 1 by 4 pi epsilon naught Q1 Q2. So the product of the charges divided by the radius, the distance between the nucleus and the electron. So here, what are our Q1 and Q2? Q1 is basically the charge of the electron. And this time we are going to take it with the correct sign because we want to see what is the sign of the potential energy. So Q1 is minus E and Q2, the charge of the nucleus is plus ZE. Remember, Z is the atomic number times the charge of the electron. So we have to substitute Q1 and Q2 into this expression like this. And we know that radius, we know the radius formula, radius of the nth shell. So you can say radius Rn is this big expression here. So if you want to get the potential energy formula, what do we need to do? We need to substitute R in this radius, right? Using this radius formula. So we need to substitute the R over there in the formula and this Q1 and Q2. So let's work it out. So potential energy formula in the nth shell is going to be potential energy equal to 1 by 4 pi epsilon naught. Q1 is minus E, Q2 is ZE divided by R. And R will be this big expression, N square H square epsilon naught, and I'm going to take this denominator on top. So we are going to get pi m ZE square. So we have this massive formula for the potential energy in the nth shell. So let's see if we can simplify some things here. So you can see the pi and pi is going to get cancelled here. And I don't think there's any much simplification we can do. So let's see what is our final formula working out to be for potential energy in the nth shell. So potential energy in the nth shell is working out to be, there's a negative sign minus. We'll talk about that because why is the potential energy negative? And I'm going to bring all these expressions here. So m, the mass, E square, there's a E square there. So E to the power 4 divided by 4 H square epsilon naught square. And then we are left with a Z square divided by an N square over here. So this is the potential energy formula in the nth shell. Now let's compare this formula with the kinetic energy formula in the nth shell. So if you saw kinetic energy formula, again we had a Z square N square M E to the power 4 H square epsilon naught square. The only difference is there's a 8 over here. And of course here the sign is positive, kinetic energy is positive, potential energy is working out to be negative. So two main differences, here it's positive with the 8 over here, here everything else is the same, but you have a 4 over here. Okay, so if you want to compare this potential energy with the kinetic energy, maybe I can change this to an 8. So I'll multiply the denominator and numerator by 2. So what will we get over here? Minus 2 m e to the power 4 divided by 4 h square, sorry 8, you multiply it by 2, right? So 8 h square epsilon naught square times z square by n square. So you can see it is basically minus 2 times the potential energy formula, right? So you guys can see it is minus 2 and this entire expression is the potential energy formula. So we get a very interesting thing here that the potential energy in the nth shell is minus 2 times the kinetic energy in the nth shell. Or if we use that expression that we had learned, so we'll get, if we use the shortcut formula, potential energy in the nth shell will be minus 2 times 13.6 Z square by N square electron volts. So this is a very interesting thing we have got, that potential energy, this is the final shortcut formula, and it is minus 2 times the kinetic energy in the nth shell. Now why is the potential energy negative of an electron? Kinetic energy is positive, right? Half mv square. But why negative? See, negative we got because there is a negative charge here and a positive charge of the nucleus. But the reason of this negative potential energy is because when the electron goes very far away from the nucleus, then the energy of the electron is considered to be zero. So let's say electron is at infinity. So we say there is no attraction, so the potential energy between the nucleus and electron is zero. And when you bring the electron close to the nucleus, do you need to give it energy or does it lose energy? So we know that to remove an electron from the atom, so to take it from the nucleus to infinity, we need to supply energy, right? And so reverse, when electron comes from infinity to the nucleus, that means it gives away energy. But at infinity, its energy is zero. So if it keeps on giving, let's say, 1 electron volt, 2 electron volt, 3 electron volt as it comes down, it is becoming minus. So that is why it makes sense that electron's energy, the potential energy of the electron is negative, because by reference at infinity, very far away from the atom, it is zero. So when it comes closer to the nucleus, it is a negative energy. So remember this explanation. So it is absolutely fine that the potential energy is negative, kinetic energy is positive. Now let's talk about the total energy of an electron. We know an electron has two types of energy: kinetic energy due to its motion and potential energy due to the electrostatic force between the nucleus and the electron. So total energy is going to be the sum of potential energy, PE, plus the kinetic energy, KE. And we have derived formulas for both of them. So let's go ahead and substitute the formulas. Potential energy, we saw our formula was minus 2 times 13.6 Z square by N square. Remember, potential energy was negative and it had a multiplication factor of 2. And kinetic energy was 13.6 times Z square by N square. And these are all in electron volt units. So go ahead and simplify this. So you can see that there's a minus 2 and this entire term is same. So it's like a minus 2x plus x. So obviously you'll be left with a minus x, minus 2x plus x. So we are left with minus 13.6 times Z square by N square electron volts. This is the total energy in the nth shell of the atom. And once again, see, the total energy is negative because remember, if you take the electron very far away from the nucleus, the potential energy is considered zero. But when you bring it close to the nucleus, the potential energy is basically negative, right? Because as it comes close to the nucleus, it keeps on losing energy, because to remove it from the nucleus, we need to add energy. So as it comes close to the nucleus, it loses energy, and that is why this total energy is working out to be negative. So let's apply the total energy formula for the electron in the hydrogen atom. We'll look at the energy of the electron in different shells: first shell, second shell, third shell, and so on. Remember, the total energy is minus 13.6 times Z square, the atomic number square, by N square in electron volts. So let's go ahead and find the values for the first shell. In the first shell, we know N equal to 1. And since we're talking about the hydrogen atom, what is the atomic number? That's right, it has only one proton, simplest atom in the universe. So atomic number is 1, Z equal to 1. So the first shell will have how much energy? So energy in the first shell, the total energy we can say, or we can just write E1, the energy of the first shell is going to be minus 13.6 times 1 square divided by 1 square. right? Atomic number is 1 and the shell number is 1. So 1 square plus 1 square, that means obviously the answer is going to be minus 13.6 electron volts. That is the energy, total energy of the electron in the first shell. Similarly, what is the total energy of the electron in the second shell? N equal to 2. This is our E2. So E2 is going to be minus 13.6 times Z square, which is 1 square divided by 2 square. N equal to 2. So if you guys calculate this, how much will you get? You'll be getting minus 3.4 electron volts. This is the energy of the electron, total energy in the second shell. Now let's look at the total energy in the third shell. So in third shell, we know N equal to 3. E3 is going to be minus 13.6 times 1 square divided by 3 square. Atomic number 1, shell number 3. So if you substitute these values and do the division, you'll get minus 1.51 electron volt, the total energy in the third shell. And let's look at the total energy in the fourth shell. In the fourth shell, we have N equal to 4. So simply we'll get E4, the energy in the fourth shell is going to be minus 13.6 times 1 square divided by 4 square. So if you calculate this, you're going to get minus 0.85 electron volts. And these are all the energies of the first shell, second shell, third shell, fourth shell in the hydrogen atom. It is useful to remember these values, okay, because you'll see them again and again and they are used in questions. So you should learn up these 4 values of the total energy of the electrons in the shells of the hydrogen atom. Now, as you can see, when we are going from first shell to second shell, third shell and fourth shell, can you see that the energy of the electron, is it increasing or decreasing? The answer is it is increasing because the negative value is becoming smaller. See, in the first shell, it's minus 13.6, then minus 3.4, then minus 1.51, then minus 0.85. So the energy of the electron, the negative number is becoming smaller. That means energy of the electron is increasing. Because remember, as you take it to a higher shell, you need to give it more energy. As the electron goes further and further away, its energy will increase. So minimum energy in the first shell, and as you move it ahead, go into higher shells, total energy of the electron increases. So we discussed the total energy of the electron in the nth shell. If I ask you, when is the energy of the electron maximum? In which shell number? So as we saw that as the shell number keeps on increasing, as we saw when the shell number keeps on increasing, the energy of the electron is also increasing because the negative number becomes smaller. So we can say that as you're going to a higher and higher shell, so we can say as the n increases, total energy of the electron will increase. And this you can see from the expression itself, because energy in the nth shell is minus 13.6 times z square by n square. So as the shell number increases, this negative term becomes smaller and smaller. That means we have highest energy. So when will it be maximum? We can say when the electron is very far away from the nucleus. Of course, the atom is a very tiny particle. So very far doesn't mean, 1 kilometer. It may be a few centimeters, right, for the atom, because atom is very, very tiny. So basically we can say that when n is infinity, that means you're very far away from the nucleus for the electron. When n is infinity, so in the total energy of the electron will become what? If you divide by infinity, total energy of the electron is 0, which we can say is the maximum energy. And in this case, we can say the electron is free from the atom because it is very far away from the nucleus. So the atom has become an ion because it has lost an electron. It has become positively charged. It's become a cation. So this is when the energy of the electron is going to be maximum, when it is very far away from the nucleus. So till now, we have done the first 2 postulates of the Bohr's model. Remember, the first postulate said that when electrons revolve around the nucleus in fixed circular orbits of fixed radius, they move with fixed energy. But then the third postulate talks about that electrons can also gain or lose energy when they change their orbits or when they change their shells.
So now we are going to look at the third postulate of Bohr, which says that electrons can gain or lose energy when they are shifting the orbits. If they are in the same orbit, the energy level will be same. That's why they are called stationary orbits, right? Stationary energy levels. But when they shift, then they can gain or lose energy. So let's understand this in more detail. So Bohr's third postulate said that electron can gain or lose energy. So let's see what happens when an electron gains energy. So let's say the electron is in the first shell of the atom. Let's say it's in the K shell. So when it gains energy, where do you think it's going to go? Obviously, it is going to move to the higher shells, because remember, the energy of the first shell, the total energy is minimum there, and as you go to higher shells, the energy increases. We are using negative values, but we know that negative values keep decreasing. That means energy increases. So when an electron gains energy, it says, yeah, I've got some extra energy, so I'm going to move to the higher shell. So let's say it goes to the second shell, or let's say it's go to the third shell, and so on. And this is called excitation of the electron. So you can note that down. When it gains energy, we say it is called excitation of the electron. Because when you get energy, you get excited, right? Like when you have some chocolate, or you have your, you have a cup of tea or coffee, you get energy, you get excited. So same way the electron moves to a higher level. Now what will happen when the electron loses energy? So if you take away energy, obviously it will be the opposite. So let's say the electron was in the third shell and it loses a certain amount of energy, which we're going to talk about. It will drop down, right? It will come down, let's say, to the second shell, or it may come down to the first shell. And this is called de-excitation of electron, opposite of excitation. So let's write that down. When electron loses energy, it is called de-excitation of electron. So this is the important concept here. When an electron gains or loses energy, it cannot stay in the same shell. Because remember, in the shell, the energy is fixed, right? Because every shell has an energy level. But when it gains energy, it's called excitation. It will move to higher shell. Or if it loses energy, it will come down, right? It will move to the lower shell. That is called de-excitation of electron. As we have discussed, when an electron gains energy, it will move to a higher energy level. And when an electron loses energy, it will come down to a low energy level, right? But now an important question is, how much energy will the electron want to gain or lose? So there's one interesting point here, that how much amount of energy will it want to accept? So let's say the electron is in the first shell, okay? So our electron is over here and we give it some amount of energy. That means we are causing an excitation of the electron. So definitely it will want to move up to a higher level, okay? So let's take an example. Let's say you give it 10 electron volt of energy, okay? So the current energy of the electron is, energy in the first shell is minus 13.6 electron volts. And you give it an extra 10 electron volt of energy. So what will be its final energy? So if you add 10 electron volts over here, what will you get? Minus 13.6 plus 10. So that is minus 3.6 electron volt. So will that be sufficient to take it to the second shell? The answer is no, because the second shell has a level of minus 3.4 electron volt. And here I'm using the values for the hydrogen atom, right? So we are talking about the hydrogen atom here. So if you give it 10 electron volt of energy, it will say thank you, but then no thank you. Why? Because it is not able to go to the second shell. So it will fall back into the first shell. It cannot accept this energy level. It's exactly like a video game. If you have played Prince of Persia or Mario, you know that you have to do the right amount of jump to move to the next level, right? So when the character has to have the right amount of energy to go up, otherwise it falls down and then you try again. Same thing will happen. So this is like a video game that the electron is playing. It needs exactly the right amount of energy to go to a higher shell. So if 10 electron volt will not work, how much will work? You can easily calculate it by simply doing a subtraction here. So you can calculate it yourself. You just have to do minus 3.4 minus 13.6.
Since both values are negative, you can just take the difference. So if you calculate it, 13.6 minus 3.4, how much energy does this guy need, the electron? Correct, 10.2 electron volt. So if you give it 10.2 electron volts, then it is very happy because now it can go to the next shell. Similarly, you can calculate how much energy is needed by doing a subtraction of 13.6 and 1.51. It will take exactly that amount of energy to go to the third level, just like your video game character. So this is what Bohr said, that when it is moving to a different energy level, you have to look at the difference in two energy levels. An electron is not ready to accept any amount of energy. It has to be exactly equal to the difference in two energy levels. So we can write that as delta E. The difference in energy level is your final energy minus the initial energy. So you can write this as final minus initial. And that means there is a quantization over here. Why? Because the electron accepts only certain energy values. It will not accept 10 electron volt, 9 electron volt, some random value, or 10.1. It will exactly accept 10.2. Even 10.3 will not work. Okay. So it must get the right amount of energy so that it can move to the higher level. Otherwise, it will not be able to do that. And same thing when it is coming down, right? So you can apply the same logic when the electron is getting de-excited, when it is losing energy and coming down, again you take the difference. And once again, it will be only those fixed values. So you can easily calculate if it is coming from the third shell to second shell, how much energy does it need to lose? Very easy. You just do the subtraction of these, okay? And keep the correct sign. So it will be your minus 3.4 minus 1.51. So you guys can calculate it and see how much energy it will lose. So remember this video game example, and this is exactly what is happening. It needs the right amount of energy, gain of the right amount of energy to go up, or lose the right amount of energy to come down to a lower shell. And this is what Bohr said in his model. Remember, another major drawback of Rutherford's model was that it could not explain the atomic spectrum, or what we call as the line spectrum or discrete spectrum of atoms. For example, if you take hydrogen gas and if you heat it, right, or you give it an electric discharge, the scientists noticed that it forms this kind of line spectrum. You see these beautiful lines, but only of certain colors, only of certain wavelengths. It is not like this continuous spectrum where, you know, the Vibgyor spectrum which you are familiar with. We call it Vibgyor, the 7 rainbow colors, but we know that it is a full continuous spectrum having all these infinite wavelengths or infinite colors. But the hydrogen gas, or any other gas for that matter, has this kind of line spectrum or discrete spectrum where you can see only certain colors. Now, why is that? Remember, we just talked about that electrons will accept, gain or lose only certain amount of energy, not any value that you want. And when it loses this energy or it gains energy, it can be in the form of electromagnetic radiation, what we call as light, or even beyond the visible spectrum, right? And so when this energy is lost, right, when energy is released, then you will see that electromagnetic waves of certain colors, of certain frequencies are visible. And this is what Bohr was able to successfully explain. We'll be talking more details about atomic spectrum in our next video, but let's finish off with the Bohr's postulates here. So the fourth postulate of Bohr's model said that the frequency of radiation absorbed or emitted during these transitions. So when electron moves from, one shell to the other, then as we discussed, energy is absorbed or emitted, and the frequency can be calculated using this formula. Frequency F equals delta E. Remember, we talked about change in energy divided by H. Who is H? H is Planck's constant. And remember, Planck's constant has this value H equal to 6.626 times 10 to the power minus 34 joule second. So if you know the difference in energy levels, then you can work out the frequency of the electromagnetic waves emitted or absorbed using this formula. So just divide the difference in energy with the Planck's constant. So delta E by H will give you the
frequency of radiation. You can also calculate the wavelength of radiation by using the formula C equal to F lambda, right? Or velocity of the wave is equal to frequency times the wavelength. So this fourth point explains the atomic spectrum. Why we see these certain lines or these certain energy bands of a fixed frequency. But we'll be talking more details about atomic spectrum in our next video. So I hope Bohr's atomic model is crystal clear to you now. Remember, there were many atomic models proposed over the years by the scientists. It all started with John Dalton proposing the model of the atom in 1807, where the atom was considered like a sphere. And then J.J. Thomson refined it and proposed the plum pudding model in 1897. Then a few years later, Rutherford proposed the famous nuclear model in 1911 with his alpha scattering experiment. Then we discussed there were drawbacks of Rutherford's model, which were corrected by Bohr's planetary model in 1913. And this is the model we have discussed, Bohr's planetary model or Bohr's atomic model in this video. But were there any drawbacks of Bohr's atomic model? The answer is yes. There were some limitations. Do you know what they were? Do research and let me know your answers by putting it in the comments below. I look forward to reading your comments. And then finally, we have Schrodinger's quantum model, which was proposed in 1926. That we'll talk about in a different video. So hope you guys enjoyed this video. Do hit the like button if you did and share it out with your friends. And if you haven't subscribed to our YouTube channel, come on, what are you waiting for? Hit that subscribe button right now and click on the notification bell so that you don't miss out on any of our videos. And do check out the full courses on our website manochaacademy.com and our Android app. I'll put the links below. We have full courses on physics, chemistry, biology, maths, coding and artificial intelligence. In these courses, you're going to get live classes, concept videos, quizzes, questions, mock tests and revision notes. So what are you waiting for? Do check it out. Links are given below and please do share it out with your friends. So stay connected with Manocha Academy and just keep learning.